the competitive Swiss National Science Foundation Postdoctoral Fellowship. He earned his PhD from École Polytechnique Fédérale de Lausanne, EPFL, under the supervision of Anna, how do you say her? Fontcuberta, focusing on the development of germanium tin materials and devices for next generation single photon avalanche detectors and telecommunications. His research lies at the intersection of experimental science, computational modeling, and machine learning for materials discovery, which you all will hear about today. And in his free time, Andrea is an incredible photographer, climber, hiker, and nature enthusiast in general. So without further ado, I'm excited to welcome Andrea.
Thank you very much. Well, thank you all for being here. This is amazing to see such a nice turnout. And thanks for the introduction, Lauren. So I'm here today to give some brief introduction into the efforts of the community towards accelerating experimental material science using automation and AI, and then delving into a bit more into the specifics of my work on automating compositional analysis of powder materials. So material innovation is one of the pillars to accelerate the green transition. And thanks to the computational power that we have at our disposal today, we can use electronic structure calculations and AI tools in order to screen and look for compounds that could potentially replace what the materials that we're using today, both in terms of performance and in terms of sustainability. And we now have thousands of compounds that have been hypothesized and proposed, but the real bottleneck lies in the experimental synthesis of these materials. First, because most of the times we don't know if they are actually synthesizable or not. We may use some thermodynamic descriptors like the energy of formation, which sometimes works, but a lot of times doesn't work. So we don't have an established way of knowing this. And secondly, even if we think a material is synthesizable, we actually don't know how to make it. And so the experimental synthesis of a material proceeds through a series of trial and error steps, which are inefficient, may take a lot of time, sometimes months, sometimes years. Sometimes you're lucky, it can take very little, but most of the times it takes a long time. And so experimental data is in general time consuming to collect. And so for this reason, there are some groups, including ours, that are working towards trying to understand and model experimental synthesis better and try to become more predictive with the goal one day of being able to literally calculate the recipe of a hypothetical compound. But so far, we don't have these tools yet. So a common approach is that of automating the experimental synthesis of materials. This is because it increases the throughput, not necessarily because machines do things faster than humans, but mostly because they can do them in batches sometimes. And most importantly, they can work 24/7, while your undergrad student at some point has to go home. And secondly, if machines are well designed, they're also more reproducible, especially when it comes to replacing manual operations like applying pressure, turning a knob. And so if they're well designed, they can be much more reproducible. And second approach is that of also including artificial intelligence, both for data analysis to speed it up, to automate it, but also to make it more powerful, to see patterns that the human brain cannot see in the data. And also, most importantly, using AI for decision making and guiding the experimental synthesis or experimental material science in general. This is done through what they're called active learning algorithms that are able to model the system we are exploring and propose new experiments, updating then the model with the experimental outcome, and then propose a new experiment and continuing this in a loop until the desired target is reached. And when we combine automation and AI, we get autonomous closed loop discovery, where the AI communicates with an automated setup and drives the experiments, takes the new data, and continues until convergence. And an example of such closed loop discovery is that of ARIS, which stands for Autonomous Research System, that was built in 2016 at the Air Force Research Center, where this group coupled a chemical vapor deposition system for carbon nanotube growth with an active learning algorithm in order to learn the dependence of the growth rate of the carbon nanotubes in function of experimental parameters, such as temperature, gas pressure, and gas composition. In this case, this group used a random forest model to model the growth rate in function of the parameters, and they used some genetic algorithms to propose parameters that were thought to lead to a target growth rate. And they updated the target growth rate in a function of the experimental numbers. And after a few hundred of experiments, they were able to converge to a random forest model that captured the whole dependence of the growth rate on the experimental, experimental parameters. Today, the most standard active learning algorithm that is used is actually Bayesian optimization. That uses a probabilistic model to model whatever target property we're trying to explore. It models it in function of the experimental parameters, assuming that this property changes smoothly in function of these parameters. But most importantly, it's a probabilistic model, which therefore includes uncertainty and is therefore able to, it knows in which parts of the parameter space it actually doesn't know or is not sure about the prediction. And therefore, using this uncertainty, it can more efficiently probe the experimental space in order to complete the information and reach reach the global maximum, like maximizing the property that it's targeting in a lower amount of steps. In this work from 2020 from University of British Columbia, the authors coupled Bayesian optimization with a robotic arm for synthesis of organic thin films with the target of maximizing the whole mobility of these films. They varied the dopant concentration of the polymer and the annealing time, and they could explore this 2D parameter space in a more efficient way, maximizing the whole mobility faster than they would have taken simply by random sampling or sampling the space in a grid. But in this case, their automated setup only works at the material level. There's a tendency of going now towards whole device assembly, because often the material properties are important also in the context of coupling to the other components of the device. And this group at Forschungszentrum Jülich in Germany built a whole setup for assembling organic photovoltaics and testing them in situ, within the same setup. And with this setup, they could explore a 10-dimensional parameter space that included varying the active layer, the active photovoltaic layer, varying its processing conditions, but also varying the various electron transport layers and conductor layers and the processing of these layers. And doing so, they could explore the parameter space in a much more efficient, much faster way than what could be possible to do manually. And lastly, the latest trend is that of coupling this closed loop discovery with large language models, not only to give instructions and to communicate with the setup, but also to, for example, include the experimental knowledge that is already in the literature. In this example, I show a work that just came out from Julie's group at MIT, where they assembled CREST, which stands for Copilot for Real World Experimental Scientists, where they cleverly looked for new catalysts to maximize the activity of formate oxidation. And they looked for this catalyst in a compositional space of 8 different metals. And instead of using standard Bayesian optimization, they looking simply in the blindly, let's say, in the compositional space, in this 8-dimensional compositional space, they actually use Bayesian optimization to search in a latent space that was built embedding the knowledge that was already present in the literature about the activity of catalysts within the experimental, within the compositional parameter space they were looking for. So they literally took pieces of papers where they talked about this catalyst activity and used word embedding models to construct vectors of 1,000 dimensions, and then used only the principal components of the space to search for this catalyst. And because they had already some this knowledge was embedded in the system, they could converge to the global maximum of their space in a much more efficient way than simply using standard Bayesian optimization, which would have been blind on the already developed experimental knowledge on the system. And this worked, of course, because there was already a lot of information on the formate reactions in the literature in this compositional space. So with this, I just wanted to give a brief overview of some of the tools that are used to accelerate experimental material science. And I would like now to go to what we are doing within our lab at Ceder Group. Before I arrived in the group, some very clever colleagues of mine assembled the A-Lab, which is an automated setup for solid state synthesis. Solid state synthesis means, in brief, taking powders of different chemistry, mixing them, putting them in a furnace for them to drive a chemical reaction. And this is a process that is used widely in industry, for example, in energy storage and conversion, for example, batteries, applications, and a lot of other different technologies. In our setup, it's the whole process of synthesis is fully automated, from the dispensing and mixing of powders to creating a slurry, mixing with ethanol, the powders, drying the slurry to evaporate it, transferring the slurry to a ceramic crucible, drying the ethanol out of the slurry, and then transferring the crucible to the furnace, driving a reaction, retrieving the powders, and preparing samples for characterization, and then running the characterization steps. As I said before, we do a lot of synthesis science, meaning that we really try to model what happens during the reaction. And therefore, for us, it's really important, and in general, it's really important because, for us, it's really important to know exactly what phases we have in a product of reaction. This is, in general, really important because all the phases we have in our material influence its properties. And ideally, because we're working in a high throughput environment, we want to obtain these phases rapidly. The workhorse of powder characterization is X-ray diffraction that to probe the crystal structure of our powders. When we run X-ray diffraction on the powders, we get a pattern like this full of peaks, and we can try to match these peaks to structures that are already known in the experimental database. And for this, 2 colleagues of mine, Yuxing and Matt, Yuxing is here too in the audience, have worked on automating this process. They built a solution that uses a tree search to explore the full solution space to find what phases may match your pattern. And they use structures from the experimental data collected in the inorganic crystal structure database. And then at each step, they try to find they try to match the major peaks, try to find what phases match them.
I think we need the.
Is this the remote? Is this the TV?
Yeah.
Or
Yeah.
You can go down and then you press later.
the smart TVs?
The smart.
Yeah.
It's not touch.
Oh,
I'll mess around with it. While you
Okay,
talk.
thanks. Yeah, so and then the odds, they try to match the remaining peaks and going on. So going forth, they can get to a solution where they propose different a combination of different phases that may match the pattern, and they cleverly, because oftentimes it is not possible to unambiguously individuate the phases that are in your pattern. Dara actually, thanks, Lauren. Dara actually tells the user that he found multiple possible patterns, and so that some decision making can be done after to try to understand which patterns are actually in your material. And so you've seen here that in a XRD is extremely useful and it's essential, but it does not allow most oftentimes to unambiguously define what phases you have in your powder, especially when you have multiple phases with overlapping peaks, or when you have sometimes we're trying to make new materials, so the structure of this new material is missing from the database, or sometimes we may have amorphous phases to which XRD is not sensitive. And for this reason, we need to complement the crystal structure with compositional information. And the issue is that there's none of the established techniques allow to get compositional information at the single phase level accurately and in high throughput. They either deliver fast average composition or more slowly phase level composition. And so for one promising technique is energy dispersive X-ray spectroscopy at a scanning electron microscope, because it's fast, it has a decent sub-micron resolution, spatial resolution, and it's cost effective. However, until today, if used on as deposited powders, it would yield large quantification errors. And for this reason, it's not really been used to rely on quantitative compositional measurements in powders. For this reason, I have worked in the past year and a half on trying to make this process more quantitative on as deposited powders, and then combine it with automated acquisition and machine learning analysis to deliver a framework called automated electron microscopy X-ray spectroscopy that allows to get fully automated, accurate composition analysis of powders at the phase level, although the human is out of the loop. So I just want to give a brief recap first of SEM-EDS to make sure we're all on the same page. In this method, we have our sample in a scanning electron microscope. We shine our sample with an electron beam. The electrons from this beam will interact with the material in a volume that we call the interaction volume, whose dimension is anywhere between a few hundred of nanometers to a couple microns, depending on the material density. And as the electrons travel in the material, they can occasionally collide with an atom, knocking out an inner shell electron, leaving a vacancy behind. This vacancy is then filled in by an outer shell electron that as a result of this transition, and a photon of the energy of an X-ray is emitted, and its energy is exactly equal to the difference in the energy between the two electronic states. Therefore, the energy of the X-ray is really characteristic of the element from which it was emitted. So if we couple the scanning electron microscope with an energy dispersive detector that literally counts the X-rays in function of their energies and builds an histogram, then depending on the position of their peak, we know what element it belongs to. Now, we can actually get the full composition, not only what elements we have inside, by measuring the intensity of these peaks, and we can obtain the mass fraction individually for each element in a bulk material, in a bulk sample, meaning that the volume of X-ray generation is fully contained within the material, and in a flat, polished material. We can use this very simple relation to get the mass fraction of each element by dividing the intensity of our peak by the intensity of that we have measured in a standard unknown composition times some correction factors that account for the different intensity in function of the composition of our material and the difference in composition between the
So
standard.
does it give you structural information or just?
Structure, no, just composition. Yeah. So this formula has been around for 70 years. It works very well when you have a bulk polished material, but our powder samples, they're not bulk and they're definitely not polished. And this complicates the picture a lot because the particle geometry affects the peak intensities, and it does so due to two main effects. The first is the mass effect, which occurs when the volume of generation of X-rays is not fully contained within your particle because your particle is too small, and therefore you lose some intensity. And the second effect is the absorption effect, which causes the peak intensity to depend on the actual position on which you measure on your sample, because depending on the position, your X-rays will need to travel a different absorption path length before reaching the detector, and therefore it will be absorbed on the way differently depending on where you're shining your particle. So this means that you cannot simply use the measured intensity when you collect a spectrum from a particle. Otherwise, you'll get huge errors, and we're talking like 100%, 150%. It's like literal, the composition may literally be nonsense. But luckily, there was someone in the 80s that had a very clever intuition that understood that we can actually take advantage of the continuum or bremsstrahlung X-rays, which are the X-rays that are generated as the trajectory of electrons is deviated inside the material. And these X-rays are what constitute, they are generated at all energies, and they make up the background of our spectrum. And these researchers understood that the continuum X-rays are generated approximately within the same volume of material as the characteristic X-rays. So this means that whatever scaling the intensity scaling the characteristic X-rays will suffer, the same scaling the continuum X-rays will see. So the ratio between the characteristic to the background X-rays at a given energy is constant. And therefore, it's almost independent on particle geometry. And this is the approximation that we use in order to be more quantitative about about SEM-EDS collected from powder samples. I'm not going to go through the details, but I just want to show the process quickly. When we collect the spectrum has to be fitted with some empirical models and some physics-based functions. And then we measure the peak to background ratio at each of our elements. And we use this formula, which is a slightly modified version of the previous formula, where instead of having the pure intensity of the peak, we have the peak to background that we measure divided by the peak to background that we have measured in a standard of known composition times some second order correction factor very close to 1 times a very important correction factor that accounts for the difference in generated background due to the different composition between our sample and the standard. And this is really the key correction factor that can vary anywhere from 20% to 400%. And that's what I've worked on to find a form of this factor that actually enabled us to get quantitative composition measurements from powders.
What do you compare to know if you're accurate?
I'm gonna get there, yeah. So we'll still have to consider, though, that this whole formula is based on an approximation, and therefore we cannot ignore the errors that will stem from the quantification of these spectra. But luckily, we're measuring the mass fractions individually at each element, meaning that the total mass fraction we're measuring is not enforced to be 100%. So we can actually sum up the mass fractions that we measured and see, and they can differ from 100%. And this difference from 100% is called analytical error. And it gives us a built-in metric to understand how reliable is this compositions that we have measured. Because you can imagine that if we measure a total mass fraction of 120% or 60%, there must be something wrong with the measurement we've done. The mass fraction has to be 100% or somewhat around there. And therefore, with this in mind, we use a strategy that of two-step strategy, whereby we collect tens of spectra for each sample in order to average out quantification errors. And then we filter out all the compositions that were measured that have analytical error larger than 5%. So we only keep the compositions between that have a total mass fraction between 95 and 105%. And what better way to collect tensor spectra than automating the whole process? Otherwise, it wouldn't be feasible. The framework starts with after the sample has been loaded in the SEM, we just takes as input the position of this aluminum stub. The powders will be deposited on a carbon tape, which is detected, and then divided into a frame. And we use each tile of this frame to look for particles. Because we're using backscatter detector, we have a Z contrast, and therefore our light element carbon tape will always appear darker, and we can therefore use simple intensity thresholding to segment the particles. And then the framework picks one particle at random, zooms on it, picks up to 5 points to measure EDS spot spectra, so not maps, but spot spectra, and keep making sure that they are far from the edges to minimize the mass and absorption effects. And then it goes to the next particle and keeps going, keeps looping until basically we have collected enough spectra, taking about 20 to 30 minutes per sample or 100 spectra, which is normally what we collect. And then once we have done this process, the spectra are fitted, quantified, and the compositions are fed to a k-means clustering algorithm to identify how many phases we have in our sample and what is their composition. In this case, we use clustering, assuming that compositions that are really similar will come from the same phase and will be different due to experimental error or some small dishomogeneities in the material. And as we said, we only give, the points that we give are only the ones with low analytical error, and we use the elemental fractions as features. And in this example here, I show the measurements we've done on a single phase material with sodium, zirconium, tantalum phosphate from synthesized by my colleague Bernard. You can see that all the compositions, so in this 3D plot where we're plotting the sodium, zirconium, and tantalum atomic fractions, you can see they're all very close to each other. And if we zoom in and then filter out the phases with high analytical error, we are left with the green points. And then at this point, we feed this compositional data to the clustering algorithm. Here in this case, we trivially only have one cluster, and we use the centroid of the cluster, which is the average composition within the cluster, as the output composition for this cluster, with uncertainties being given by the standard deviations. And you can see in this case that the measured composition is really close to what the stoichiometric, to the stoichiometry of this phase. And this framework actually works with, we can input candidate phases that we may think may actually be present in our sample, and the AutoEM-XSP will try to see if any cluster will match any of these, if the clusters will match any of these candidate phases that we provided, based on the distance in the compositional space between the centroid and the composition of our candidate phases. And in this case, because the compositions are so close, it found that this phase matches the cluster, and also gives a confidence score based on the distance, which is very high in this case because the compositions are practically the same. And you can see that a lot of the gray points that are far from the cluster, indicating that the analytical error was effective in filtering out these points that were not that were yielding incorrect compositions. And then to get back to your question, then Daniel, we have evaluated the accuracy of this framework on 74 different single-phase compounds that encompassing compositions with 38 different elements scattered across the periodic table, whose stoichiometry was known. And we have build statistics based on the relative deviation from the expected value of the single atomic fractions within each composition. Which is just another fancy name for relative error. And in this plot, we see the distribution of these relative errors in function. So for all the atomic fractions, only considering the spectra that were deemed to be reliable, so with a low analytical error. And you can see that we obtained in 60% of the cases, the relative error was lower than 5%. And in more than 80% of the cases, the relative error was lower than 10%. And this is nice, but you can see that we still have a lot of outlier points. And if we only collect a few spectra from the phase, we may end up with a large error. However, if we only look at the points that we measure at the cluster centroid, so this one is all the points, this is only the atomic fractions measured, extracted at the centroids, which are the output of our framework, you can see that the statistics improve visibly, and we have 76% of the atomic fractions with a relative error lower than 5%, and more than 90% they have a relative error less than 10%. Yeah.
So it says N, O, and F. So those are the light elements. So you're showing your better error is on light elements in this plot?
No, it's basically the same distribution, I would say. Like they also follow the same kind of distribution.
Right, but they're narrower, right? Isn't that, the lighter peak is narrower, so that's got the higher.
I think it's narrower because we have less counts. But
Okay.
maybe slightly narrower, but that's also because most of the light elements, they have large atomic fractions because they are most predominant in terms of atomic fraction. And it's easier to get lower errors when you're measuring higher atomic fractions than lower atomic fractions. So that's the reason why we see that we have some narrower distribution. But yeah, I distinguished the two because I wanted to show that we're also able to quantify light elements reliably, which is actually a very long-standing challenge in the SEM-EDS.
So clustering means you're basically averaging over everything.
So far I've only showed one cluster, so that's all it is for the moment.
Yeah. But you're taking the centroid as your prediction.
Yes, which is nothing else but the average. Yeah. And then, I mean, if we look the absolute error, we also have 90% of the cases where we have an absolute error lower than 2%, and in more than 70% of the cases lower than 1%. So we are being quite really accurate on our compositional measurements. And we can see here that really clustering and averaging over multiple points is really essential in improving the accuracy.
Not sooner elemental composition is the material you added in?
Yeah, so we have three classes of materials. One is commercial materials. So I just take the stoichiometry that is given. One is minerals, which are provided by John behind there. They are used regularly as EDS standards in the Earth Science department here. And therefore they have been measured and remeasured. So I just took the stoichiometry as given. And then we have materials that we have synthesized ourselves. And those ones we have refined with XRD and a couple with inductive coupled plasma mass spectroscopy, spectrometry. And yes, we took the stoichiometry, which means that we're not considering, they may have slightly different stoichiometries, but I've looked at the separate statistics, they don't really change. I mean, these numbers change slightly, but they still remain around 75 and around 94, even if I just take the synthetic, assuming that maybe we may have some wrong stoichiometries, slightly wrong stoichiometries, because the XRD mentions very well.
From like ICP?
It's mostly XRD.
Sorry.
Yeah.
Does this include the carbon since you have carbon tape?
No, the carbon is, so if you saw the periodic table, we do not quantify carbon because we have this carbon tape. So I'm not able to discern if the signal will come from the carbon tape or the sample. So I fit it because it's important to fit it and to know that it's in your spectrum, but I subtract it after. So no, I don't quantify it. Yeah, so now that we know that we can trust the compositional data that we measure, we can use k-means clustering to look for, to analyze multi-phase samples and try to find the different phases. So in this case, I mixed two different types of manganese oxide and chromium oxide. And if I repeat the process, the k-means clustering finds actually 3 clusters, and it can find very similar compositions, and it is able to find the 3 phases that we actually have in there. Just want to point out that when we calculate the confidence score, we also take into account if there's any neighboring phase, which may decrease your confidence in evaluating how sure you are that your phase is actually the closest one. So in this case, the confidence is low, not because of the distance between the centroid and the point, but because you have Mn3O4, which is near there, which is decreasing your confidence. Yes.
So you mentioned like finding multiple phases, I guess finding a single phase versus finding multiple phases.
Yes.
In k-means clustering, don't you tend to specify?
Yeah.
And so I guess what's the benefit over like a density-based approach?
So I will show you an example later. Yeah, we have to, I skipped this, but this is the number of clusters is also determined automatically. There are some ways to do that. And first of all, what I do is that I determine whether I have a single cluster or not. And I do that based on a few empirical dimensions, which is first the dimension of the cluster, assuming it's a single cluster, because I know how accurate I am. So I know that if it's smaller than some size, then it must be a single cluster. And then I use what is called the silhouette score, which takes into account it tries to evaluate for all the multiple possible Ks. It evaluates the distance between the different clusters and the distance of the points within the same cluster, and basically tries to maximize the ratio between these two. So there's automated ways to do that, and that's what I use here. And I don't like the density approach because sometimes we have minority phases, which are maybe 1 or 2 points, and the density approaches normally discard them, while those are real points. And I know that they're real because I'm using this filtering, so I know that I can trust the composition. Yeah.
Yeah, so don't you usually have to do this in like the n-dimensional space of all the possible elements, not just 3, right?
Oh, well, we are a material science, right? So we know what elements we put inside.
Okay, so it
Yeah.
is low.
For other domains where you don't know what you have inside, that you would need to do some like peak finding,
Okay.
peak matching, which I haven't done because in material science we don't really need. And yeah, so but this is nice, but unfortunately, when we are characterizing a product or reaction, it's rarely nice isolated particles or pure phases. In fact, it's most of the times we have phases that are clearly intermixed with each other. And because our probe has a finite dimension, when we probe a region that has both phases, we'll end up measuring an average composition. And when we measure a sample that is full intermix, for example, this sample of sodium aluminum silicate intermixed with lithium manganese nickelate provided by Shilon here in the crowd, that has some micrometer intermixing, we obtain one single cluster whose centroid is, however, far from both parent phases, and that has very large standard deviations. So we're looking at very, very large variations in composition measurements, but we can take advantage of the fact that we have an automated system, collect a lot of points, and statistically, we will sample various linear combinations of the 2 parent compositions, and we can literally see that our composition, it's kind of linear combination between the 2 parent phases. And therefore, we can use algorithms like non-negative least squares or non-negative matrix factorization to decompose our matrix of measured compositions into a matrix with our vector bases. In particular, looking for using the NNLS algorithm, what we do is that we construct a vector basis matrix with all the possible pairs of candidate compositions. And then we try to fit a matrix of coefficients, which are nothing else but molar fractions. And we try to fit H such that our initial composition matrix is equal to the product of the bases times the coefficients. And If we check then the reconstruction errors, which is the difference between our original matrix and the reconstructed matrix, then we can expect that if we have a low error, then our vector, our basis matrix describes well the measure cluster, and therefore those two phases are the ones that are making up the cluster. If AutoIMXSP does not find any satisfactory pair that leads to a low reconstruction error, then it uses a non-negative matrix factorization, which is an unsupervised machine learning algorithm, where it actually fits also the matrix W and H iteratively looping one after the other until it converges. And if applying to this sample, we can see that NNLS lead finds a quite high confidence that is calculated based on the reconstruction error. It finds quite high confidence with these two parent phases, which we know are in the material. And if we actually didn't provide these two phases, NMF would actually provide compositions that are really close to what we actually have in our material, where he found some sodium aluminum silicate with cation ratios close to 1:1 and some trace manganese. And in the other, for the other phase, it also found some trace aluminum and sodium, but it found the manganese nickelate with very similar cation ratio as in the original material. Of course, the lithium is not here because lithium is not detectable in EDS. So lastly,
Why is lithium not?
it's the energy is way too low, and it gets mostly absorbed at the window of your detector and EDS. So it's really like a system limitation.
Okay.
Yeah.
That's
Or the
fascinating,
EDS,
actually.
yeah. Yeah, it generates X-rays, but they're not detectable.
Yeah.
And so to put everything together, now that we know that we have accurate composition measurements, you can use k-means to find multiple phases, and we can use NMF and NLS to decompose mixtures. Then we can actually test this framework on real world samples. And we can here report an example where we could find a residual titanium oxide in a synthetic sample, and XRD was not able to find titanium oxide, and we could find it because it was we could successfully decompose the small clusters of only 2 points, which a density, you can see the density is extremely different. It wouldn't have worked. And on the other hand, we have a very complex synthetic sample where we could find some residual precursors of titanium oxide, zirconium also intermixed. Then we could find an intermediate sodium lanthanum phosphate phase and some main phase that was similar to our target, but not quite. They could not be refined with XRD because it wasn't present in the database. So I want to conclude here with a short demo of AutoIMXSP, the measuring mineral, albite mineral. You can see it starts moving to the navigation cam to take an image to detect the carbon tape. And then it goes back to SEM mode. It uses autofocus, autocontrast, and auto brightness functions from the microscope. Then it looked for particles. It went to the first particle, determined where to measure. Now it's quantifying, which is the slowest part, especially in this computer. And then it's looping across particles. Periodically, it runs a clustering analysis to check for convergence, meaning that it's looking if it matched your clusters to any of the compositions, the candidate compositions, and it matched them with a high confidence. If not, it keeps going until basically it collects the maximum amount of spectra or it converges. And then it runs the final clustering and outputs. Yeah, so it determined albite. And then it outputs the image where it found the carbon tape and measured, then every single particle where it measured with annotating all the points where it actually measured. And then you have like a full Excel file with all the compositions where it measured what, and then the clustering. Yeah, so this is it. I want to thank you for coming today and listening to my talk. I want to thank the Ceder group and the colleagues and Bernard, Yixing, and John here that provided a lot of these 74 samples that I use for benchmarking the accuracy. I want to thank the sponsor, Swiss National Science Foundation. And then here's a preprint QR code if you're interested, and I'll be happy to take any questions if you have them.
How do you deal with like heterogeneities within like a powder sample? So like if you see like the same powder is not exactly homogeneous, like
Yeah.
how does it decide where to take a
So-
spectrum from?
So it takes it randomly, right? So that I don't bias towards any particular particle. And the idea is that if you collect enough, which I believe we kind of do, I mean, we may miss minor, like 1-2% phases. If you're collecting only 100 points, you may miss it, of course. Sometimes we collect 200 for this reason. But yeah, basically I just sample randomly and then I don't bias it towards anything and I rely on statistics.
Sort of building on that, you would be able to backtrack from those points that have a high compositional error, right? And see where the spectrum originates from.
Yeah.
Do you think it would be worth remeasuring in the vicinity of that point to see if it's an actual phase or if it was just a small contamination or something like that?
I mean, the ones that are unreliable, we just don't know if the composition is good or not, right? We just discard it.
Well, you could go back and remeasure close to that point, couldn't you?
I mean, the point is that we collect a lot so that
Yeah.
whatever we filter out, we don't care about. That's the point.
Definitely.
But actually now there's ongoing collaboration to use reinforcement learning to guide the selection of the measurements of the EDS spots to measure, to kind of train it on which ones are the good locations of the particles where you want to probe in order to decrease this amount of spectra that you are discarding. Because right now we are discarding like half of it, sometimes even more. So it's not very efficient. But because we don't really know what parts of the particles will lead to a lower analytical error. So that's why we're trying to use this machine learning approach for it to learn where it's supposed to measure, and they use that to guide.
So I did notice like in your animation that you had some bright spots, so it's backscattering
Yeah.
electrons. So in that albite, there were some iron oxides or something. There was something present.
Yeah.
That was different, and I was just
Yeah.
kind of wondering whether it was guided to the bright spots.
It's not. I started with that, but then sometimes you end up with never probing the dark phase. So actually, that's a very good point. I do it randomly, so I expect that if there are some bright points, at some point we're gonna probe a few of them, and therefore we still get the composition. But yes, a better approach would be that of literally guiding towards trying to, when he finds that a particle has different contrast, then you should try to probe all of that. That would be a better approach, but it's not implemented yet. And I'm hoping actually to, as a second part of this reinforcement learning, to also include that, like to bias it towards exploration of the particle and not only, not random,
So you constrain the elements that you look for based on experimental input
Yeah.
from the user. So do you have a strategy for looking for impurities in the sample, elemental impurities?
So the strategy right now is that, as is showing here, I do not use only the analytical error as a filter, but sometimes I have spectra that are very poorly fitted. And I know that because I flag them. And so when I have a lot of them, I know that there's very likely some element missing in my input. So there's nothing automated on that side yet.
But that can be hard when there's peak overlap too, though, right? Between.
It's in X-rays, I mean, in EDS, the peak overlap is not. I mean, you have it, but it has to be some very specific combinations. Like, especially when you only have few elements. I mean, it can happen, but there's very specific combination of elements that give completely overlap. Well, it's quite rare. But yeah, so there's nothing in, problem is that the quantification is low in our microscope computer. So it's like, it maybe takes 3 minutes just for one, so.
Could you do like a smaller subset that's like unconstrained?
Problem is that sometimes the contamination is like, I don't know, like in the samples we were looking the other day, there are, you had it maybe on 4 particles out of the 30 that we looked for.
Or like the particles that are poorly fit, like you said?
But in principle, this should be, instead of taking the elements as input, it should try to look for the peaks and then match them to, which is what the EDS softwares do. But sometimes they get it wrong.
Yeah.
So we should like find a way to do it biasing towards the elements that we know that are there, but when there's an element that is clearly out of distribution, I mean, a peak that's clearly missing, that it should be assigned, but yeah, it's not implemented.
Kind of, interact with that other software because we're using some Oxford software that seems to be spot on.
Yeah, we can. Yeah, absolutely. We can. That was actually the initial idea that I had. I haven't implemented it, but you can. The softwares are much faster at fitting, so you can actually ask the software what elements are in there. But the problem is also that our spectra, they have very low counts. So the noise is very high, and the peak matching works not as well on these low count spectra. So actually, you need to rely more on what you know that you have there, and then if you clearly have something else, then you should include it. But yes, you can clearly do that because all of this is done basically through a Python API that communicates with the microscope. So of course, you could also give it the spectrum to fit and extract whatever elements you have in there and then add them to your spectrum. Yeah, for sure. So for example, if you had to extend this to minerals where you don't know exactly what you have inside, then you could use simply, instead of implementing the peak matching yourself, you ask the software what peaks you have, what elements you have in there, and then you fit them.